overviewed that where fluid dynamics comes into play, and we will get into a bit more details and try to see that how we can have our understanding of fluid dynamics converging with understanding the cardiovascular health. So, again to recapitulate, we talked about this, but this is important in the context of what we are going to discuss. So, if you imagine the heart as a unit, it has these 4 chambers, the right and left atrium and right and left ventricle. So, in this diagram you have the oxygenated blood, that is shown by the red color. So, oxygenated blood will enter from the pulmonary vein to the left atrium, and from the left atrium by the action of the valve it comes to the left ventricle, and then from there it gets circulated by the systemic circulation. That means, over the entire body, that circulation which takes place, which distributes blood to all of the body's tissues, and then it returns deoxygenated blood back to the heart. So, it is coming at the right atrium, and then the valve allows it to come to the right ventricle, and then from there the deoxygenated blood is pumped to the lung, where the purification through oxygen exchange will take place. So, this is the overall thing, and that is how the heart and lung are very strongly connected, and because really these are lifelines of human survival. So, in this particular course we have kept the cardiovascular and the lung flow, pulmonary flow, as 2 of the major example areas. So, now when we talk about the circulatory system, there are so many arteries, veins, etc., and every artery, vein is very unique, and it is not possible to give examples of all. The idea is that we give example of something which is very, very important and at the same time not very well discussed commonly. So, the example that we talk about here is carotid artery. Carotid artery, these are major blood vessels which provide the brain's blood supply, and that is why these are very critical. So, if you look, if you talk to any cardiac expert doctor, they will talk about 2 major types of arteries. One is the coronary artery and then the carotid artery. Coronary artery is more commonly talked about being the main ones which come out of the heart, but the carotid artery is no less important because its disease causes up to 1/3 of all the strokes. And as I discussed earlier, the stroke is different from heart attack, that it is just something that blocks blood to flow to the brain. So, now if there is a carotid artery disease, or as a matter of fact any other similar artery disease, what will people do? One is that possibly by some symptom people will try to guess, but symptoms are usually vague, and vague in a sense that they can be very similar for many other diseases, like people may feel dizziness or suddenly fall unconscious for some time, they may feel tired. So many other types of symptoms are there which you cannot specifically say that it is for carotid artery disease. So, those symptoms may be triggering for you to go through some diagnostic test. Now, depending on what resource you are having, or to tell it more clearly how much money you are having, you may be subjected to different types of tests and you may actually go through those. like MRI, Doppler ultrasound and some invasive diagnostics. These are very much possible, but although these are quite advanced diagnostic technologies and they give a whole lot of information which just a ECG type of thing cannot give, but they also have their own limitations. So, this is the difference between doing an instrumentation for human body thing with an engineered thing. For an engineered thing, the instrumentation can be used to get a whole lot of other information, because an inert thing can be probed as you like, I mean that will not disturb anything. Human body you cannot just probe like as per wish. So, MRI is good, but it does not have the spatial and temporal resolution like what you get in a CFD solution. Doppler ultrasound, it has some issue with this acoustic window limitations, because it depends on the ultrasound. Invasive diagnostics are there, that means you use invasive procedure. So, you need to use this catheter and now these are expensive. Not only that, nobody will usually like to go for that, because they have certain trauma and all, people feel somehow tensed once they have to go through these tests. And whatever are these tests, you are not able to get any detailed hemodynamic parameters such as wall shear stress, deformation, etc., which are very, very important. So, if you talk to any cardiovascular doctor, it is quite clear that the doctor is not an expert in fluid dynamics, although I have seen quite a few cardiovascular doctors who do not understand less fluid mechanics, but they may not be knowing all those mathematical tools because they have not formally gone through the procedure, but they have a reasonably good understanding. But for their day to day practice, they need 3 important hemodynamic parameters, which in their language is pressure, flow and resistance. So, pressure and flow we understand, and resistance is like a cumulative effect of wall shear stress. So, pressure, flow and resistance, it comes from the corresponding electrical analogy, where pressure is like voltage, flow is like current and resistance is like resistance. So, these are, as you understand, these are gross terminologies, like when you say pressure, pressure may vary from one point to another point, flow rate may also be different in different branches, and resistance is of course locally varying, because wall shear stress is locally varying. But usually this kind of information is completely absent. So, for doctors even average value of these are very, very meaningful, because usually they have no values to discuss about this. So, to get those, CFD is important. We have seen that CFD can do fluid structure interactions, but the CFD requires inputs. So, if you take some sort of branched artery as your geometric model and put some boundary condition and get a result, you will get a result, but that will not have anything to do with any specific patient. That is something, a generic thing, that is also very important for learning the science, because learning the science does not have to be patient specific, it is just the learning the science. But when you apply it for clinical application, it has to be specific to a patient, it cannot be generic. So, specific to a patient is what you get from these, at least the medical imaging techniques, typically MRI, CT scan, etc. So, when you have these data, the important point here is that can you use that data in CFD, so that it becomes patient specific CFD. So, the entire direction in which this subject moves is like, how can you apply your generic knowledge of CFD to make it patient specific CFD, and that is what we are going to talk about for the remaining. So, connecting medical imaging with mechanistic simulations. I have purposefully written it mechanistic because it has both fluid mechanics and solid mechanics, so not just CFD. So, to do that you need a medical image. So, usually the medical image from which you get a geometric idea of what is there is the CT scan or MR angiogram. In the cardiac space, MR angiogram is very, very common. So, it is similar to MRI, but applied specifically to this cardiovascular pathways. So, this is one particular set of image. We have a collaboration on this topic with the University of Melbourne and the collaborating professors group, Professor Andrew Wee and the collaborators. They have this access of these kind of images, repository of these kinds of images from their hospital, and there is a very strong group in the hospital who are working on these, and we interface with them for this kind of research work. So, this you have. Now, there is a very important step which will convert this medical image to a geometric information or a geometric set of parameters which can be meshed for your computational simulation. So, you need to create a geometry. This is called as geometric reconstruction, because this will have some idealization. So, you take the shape and put in elements to fill up the shape and smoothen it, so that it becomes that domain only, but with a few idealizations, which is not really exactly that, but more or less that one. Then what you do is, what are the inputs that you are going to use? So, there is a very advanced technology which is called as 4D flow MRI. So, this is such an advanced technology that even most of the very resourced hospitals also do not have this. So, 4D means you have the 3 dimensional in space and also time. So, what this gives is like the fluid mechanics inside these things as visualized. So, it can give, for example, not really the velocity profile that, but flow rate at some locations and how the flow rate changes with time. So, this also we use the resources. So, it is an imaging, for example, in what you see here is a 3 Tesla MRI machine with 60 channel coil, and ECG gating was used to acquire the data, and there the imaging is following some injection of certain contrast agent to get the clear view, and what you are getting out of that is at a given location the graph of flow rate versus time. So, that is what you get, that means data which you can visually show in the graph. So, then what you are going to do with this? So, you have MRI images or 2D phase contrast MRI images, you use. So, for MRI images you can construct the geometry, and 2D phase contrast MRI will give the flow data. So, you can get the flow boundary condition. So, you now have a geometry and you have a boundary condition, and if you have reasonable idea on the properties, you can do the fluid structure interaction simulation. Now, here we have put 2 different items, one is 3D modeling, another is 1D modeling. So, we all know that 3D is the reality, right, 3D is the reality, but it is expensive. That means, if you want to run simulation in such a 3D geometry, it may take time, and if it is taking time, a doctor is not going to write a paper for which doctor is going to wait for 2 days to really get a result on the patient and do it. I mean, doctor may as well write a paper on the patient's case, but for the doctor it is more important to save the life of the patient first and then write the paper. Unlike us as academicians, we first write the paper and see whether the bridge falls or bridge is there. So, now when we do this, we have to see that can we do something which may be a bit inaccurate, but much faster. So, can we convert the 3D picture to an equivalent at least locally 1D picture. That means, it is not completely like a sort of a straight pipe, but locally pieces of such 1D capillaries. So, that is called as 1D modeling, and because 1D is not really the order is 3D. So, converting that 3D to 1D is also known as reduced order modeling. So, somehow you are reducing your sort of dimensionality. So, while doing that, and this is what I always like to do, that sometimes there is always a temptation that you have some high end items and you present the high end items, but this is like a course. So, I can just present the high end items and you can say, wow, this is fantastic, but this is not the way in which a fundamental understanding of what is going on should be developed. So, what I have tried to do within this limited scope, at least to show that how from the most basic principles that anyone going through a very serious course on fluid mechanics will know, how can you come to this kind of problem and try to solve it. So, this is something which is a principle of conservation and transport with which we started our foundation topic discussions. So, let us say you have so this is a symbol of channel of varying cross section. This is a very simplified view, not that our blood vessel is not like that have a tapering thing, it will have some different thing, but this is just like a simple drawing. So, you have something which is the system is a control mass system, that means something which is a fixed mass. So, the system is shown by the green dotted line. So, it is a collection of mass which at time equal to 0 is coincident with a region which is that red dotted line, which is your control volume, that means your fixed place. But after some time, so at time equal to T0 plus delta t, the system, which is the Lagrangian concept, it has moved to the new green line. So, what we can say is that if we keep now the control volume, so if we now consider the intersection of the initial configuration of the system and the subsequent configuration of the system, the common part of that we call it as a control volume. So, you can see here that we now have the control volume, and you have whatever is the left of that is 1 and whatever is the right of that is 2, and as per the direction in which the mass is moving, across 1 mass is entering the control volume and across 2 mass is leaving the control volume. And we are defining capital B as any extensive property, that means a property which is for the total mass, that is mass, volume, momentum, energy, etc. And we also define small b, which is the capital B per unit mass, that is called as intensive property. So, with this definition, what we are trying to do is we are trying to relate the change of the control mass to the change in the control, just a minute, change in the control volume. So, at instant t you have the system and the control volume, just they are coincident, but to make the drawing look clear, we have separated the green colored thing and the red colored thing, they are coincident at some point of time. At t plus delta t it is like this. So, at t they are coincident, at t plus delta t, if you see the last equation, which is equation number 2, your B of the system is B of the control volume, which is the red colored thing at time del t plus delta t, minus your B at 1 at t plus delta t and plus B at 2 at t plus delta t, right. So, what you are talking about is it is just the drawing, that means that you are having this green colored thing, the new green colored thing is what you have in the control volume, which is there the diagram at the top, from that you subtract 1 and add 2, right, that is what is there, simple drawing is represented there in the figure. So, now just a minute. What we are trying to do is to see the change in property in the system, how it relates to a change in property in the control volume. So, the property of the system at time t is same as that in the control volume. At time t plus delta t, we have just seen equation 2. So, we have written that. So, you subtract these two and this will give you the change in property of the system. Why we are so much interested about that is anything related to the system which is the control mass system, you can relate it with the Newton's second law of motion, because that is what in the Lagrangian framework is how the Newton's laws are stated. So, you subtract and divide by delta t and take the limit as delta t tends to 0. So, you get the left hand side, we are writing it as we can write it as total derivative. Why? Because it is the rate of change with respect to the system, but we will write its expression with respect to Eulerian variables. So, anything which is fundamentally Lagrangian, but we are expressing it through changes in the Eulerian variables, usually we use the total derivative. Right hand side, the first term is at a given location, how the b changes with time. So, that is partial derivative, because the location is fixed, and the last two terms, one is the rate of outflow and the other is the rate of inflow. Okay. So, you have the change within the system equal to change within the control volume plus outflow minus inflow. Now, if you write what is capital B, capital B you can integrate over the volume. So, if you now substitute that, and outflow minus inflow you can write in terms of a flux. So, V dot n is the normal component of flow over that area dA. So, that is the flow rate, that means velocity in the normal direction times the dA. So, the volume flow rate is the velocity in the normal direction times the area. So, V dot n, that into dA is volume flow rate, that into rho density is the mass flow rate, and small v is per unit mass. So, whatever is the last term, that is giving the net flow of the property B, that V dot n is positive if it is outflow boundary and negative if it is inflow boundary. So, automatically that out minus in is taken care of by the dot product. So, separately plus and minus is not written. So, this is what is known as Reynolds transport theorem, and whoever has done fluid mechanics has done it, but I thought that it is good to just recapitulate this. And the whole idea is that we are trying to express what is there in the system with respect to the change inside the control volume. Now, we will apply this to something, this red colored thing we imagine as a length piece of a blood vessel. So, the length piece of the blood vessel we consider from Z to Z plus delta Z. Locally it is like a unidirectional flow along Z. So, now if you apply the Reynolds transport theorem, conservation of mass, then capital B is the mass. So, if you substitute that, and so it is the dm dt, right hand side first term is partial with respect to time, whatever is the mass inside the control volume. So, that is that one, the integral of this ds into delta Z is the volume, that times rho is the mass, and the flow term is the next term. So, we are just using the Reynolds transport theorem. Now, conservation of mass is that if you have a control mass system, a system of fixed mass, the mass is conserved. So, that is 0. Then you have the right hand side what is called as the unsteady term, and the last term is the net volumetric flow rate, because whatever is coming out and going in. So, that is basically due to the net change in the volumetric flow rate. So, that is delta q. So, you divide by delta z, delta z was that axial length, you want a local value. So, you make that axial length so small that it becomes a point. So, divide by delta z and take the limit as delta z tends to 0. So, this what you get is the so called area averaged continuity equation. So, this is the continuity equation, but area averaged. And then you go for the linear momentum conservation. So, you can write the force as your capital B, and in the z direction if you are talking about your writing this equation, you write the z component. So, momentum is just the mass times the velocity. So, u z has come and mass expression is the same. And what we are also going to note that the right hand side what you are seeing the last term, that is the outflow minus inflow, and outflow minus inflow is due to the change of u as it has gone from z to z plus delta z. So, u z plus delta z minus u z is responsible for the differential flow, and that you can write in a Taylor series expansion, and we may keep the first term only, and again you can substitute that in the right hand side. So, you will get this one, this what is the net this flow when you are talking about outflow minus inflow, that is u z plus delta z minus u z. So, when you write that, so that is your net force. Now, the net force, so the right hand side in the top what you have written is the unsteady term and the advection. So, this is basically mass into acceleration, and that is equal to the force. So, force is due to two things, one is the pressure gradient. So, if you have the pressure gradient there, then the pressure gradient which is acting. So, you can imagine that you have the pressure acting on the area this ds. So, pressure which is acting on the area ds, and the effective pressure, the change in pressure. So, what you are talking about is change in velocity, similarly change in pressure. So, change in pressure just like the Taylor series, just replace u with p. So, that is that pressure gradient with respect to z into delta z. So, that is your difference in pressure, that times ds is the force. So, that is the force due to pressure, and you have a force due to the wall shear stress. So, tau wall is the wall shear stress, and the area on which it is acting is so if you have a circular thing and the wall shear stress is tau wall, and if the radius was constant, then the area on which this is acting is 2 pi r into delta z. But if it is not circular, instead of 2 pi r it will be some perimeter. So, we call that L. So, L is like 2 pi r. Okay. So, now you can equate the left hand side with the right hand side and you can get this equation. You can simplify it further and I will show that. So, now your objective, we are continuing from the previous this slide. So, wall shear stress you have to calculate, and this is where you require the velocity profile. So, to get the velocity profile, let us assume that u by u average, that is the velocity along z divided by the average velocity along z, is a function of your local radial coordinate r. So, if you now substitute that velocity profile, so if you know nothing, you can use your approximate parabolic velocity profile, which we have learned from that Hagen-Poiseuille flow. So, that in that case f is 2 into 1 minus small r square by capital R square, that all of you have done basic fluid mechanics will know this. So, this is an example, but see always there are so interesting scopes. So, if some of you are interested, you can say no, in real artery vein this will not be the case. So, what will be the case? So, you can take a better approximation. Someone will say no, why should I take a better approximation? Let me get some data from 3D simulation of the geometry used for real patients. So, some of those who are really interested will then ask a question, okay, but where will I get that real patient data? What we very commonly say, where there is a will there is a way, and this is something like this. You do not have to go to a hospital to get patient data. So, there are huge repositories of open source data. That open source data is there for two things, one is clinical research and even for fundamental research, where you do not know the name or whatever, I mean it is decoded, but you get this. So, what one can do is that if you get such data, then apply data science to use that data to get a number crunched equivalent of the 2 into 1 minus r square by r square, right. And then if you substitute that in this model, see this is why it is very important, say people who are doing in the modern era data science, if they want to apply it for a good physical problem, it is very important to understand the basic of the problem. See, I could have told you what the equation comes at the end, job is done because you can solve that equation, but you will never know where your new thing you will put if you do not know how it is derived, and that is why these fundamental derivations are very important. In your life if you want to progress in research, never ignore the fundamental derivations. There is always a tendency to do that because you can plug and pick somewhere something, the so called formula, and from our junior days we are very happy to see a formula, because formula you put value you will get answer, but that is very good for your so called exam life, but it is absolutely a disaster for innovation to do anything. So, here there is a scope of innovation, that you replace this 2 into 1 minus r square by r square with something realistic, which in the old era would not be possible to be as realistic as currently, because now you have medical imaging data, now you have data science to convert that to a number crunched function. So, instead of this f you could have another f, but if you have this f and then if you integrate, then you will get things which are functions of f. So, if you replace, see whatever is there at the bottom most, this is still very general, and only your very good choice of f means your job is done, because otherwise there is no approximation. What is there is you have integrated your governing equation over the control volume, and that is alright, I mean there is nothing wrong with it. So, in that integral expression, the only approximate thing which is giving you an approximate answer is the velocity profile. So, if you have by some way a means to give it quite well, your answer also will be quite well. So, with this particular example you can now have this velocity profile, and so with this velocity profile you can do the integration analytically and you will get that equation which is there at the top, and in that you have a velocity gradient at the wall, and to get the velocity gradient at the wall you integrate the continuity equation in the differential form, and from there you will get the value of velocity gradient at the wall in terms of the average velocity. And why average velocity is important? Average velocity is simply the flow rate by the cross sectional area. So, you can write everything in terms of the flow rate, which is your, as I told, the interesting hemodynamic parameter for a doctor, pressure, flow and resistance. So, once you do that you get your so called final formula, and this final formula is based on the f. If you change an f it will be a new formula, but this is absolutely general in that way. So, the summary is that now you have two equations, one is the area averaged continuity equation number 1 and number 2 is the area average momentum equation, which we have just seen how it is derived. So, we have assumed a parabolic axisymmetric profile. If you have anything different, you will have the algebra different, but method the same. Now, this does not close the model because you also need a physical law that will relate the pressure with the area or the radius. Yesterday I gave you a homework where I mentioned that for a thin walled cylinder, say you have that formula, the hoop stress sigma is P into R by T. Okay. So, in that way, so that means you have the stress proportional to the pressure and it is also proportional to the radius, local radius. So, here the local radius itself is also a function of pressure, right. How do you, if you recall that in that micro channel problem, how did we do it? We applied the equation of equilibrium for the solid part of the domain, integrated it and got the displacement, and that displacement we related to the pressure. From there we got the expression, and displacement will be a function of that modulus of elasticity, etc. So, a similar thing when it is applied here for a linear elastic fluid, it gives, so it is exactly the same as that one, and square root of S is because like we are talking about radius, and radius is proportional to the square root of the cross sectional area. Perfect circle is pi r square, right. So, that is how the square root of S comes. So, once you do that, so this is what is like a constitutive behavior, that means how pressure varies with local area, local thickness of the blood vessel and the modulus of elasticity. So, with this you can solve these coupled equations. The advantage is that now this is a one dimensional unsteady problem and you can solve it in a much less computational time. Whatever may be the method, time will be much less as compared to the 3D solution. So, computationally much expensive, much less expensive, and it typically takes less than an hour to complete even that carotid artery problem. So, quite straightforward. So, if the doctor gets MRI input and somehow can translate that as some boundary condition to the 1D problem, we will see how it can be given. Then to get the Q, the doctor maximum has to wait for 1 hour, which is not bad, because any investigation the reporting time is not less than 1 hour anywhere.
Sir, since here you are approximating it as a parabolic axisymmetric profile, that means you are ignoring the region where flow development is occurring. So, is there any way how we can choose that region for 1D reducing?
No, you cannot choose, simply you can approximate. So, region you cannot choose as per your liking, because your region is a full this one, full your zone, say some you have main artery and some branches are there. So, you can only consider that region for which you have input I mean knowledge about the input inflow and the outflow, which comes from the MRI thing. So, it is not as per your wish, that is what I say. No, it is very different from an engineering world, where you say I have a long pipe, I will take a part of this which is fully developed. So, here you do not have something like that. Whatever is available you have to do it, and whatever is approximate you have to be careful about it. So, clearly it has limitations. What are the limitations? The assumption is a parabolic velocity profile. These may not be valid for all scenarios as I have discussed. So, if you have boundary layer separation, or you have some maybe branching. So, you have a main artery and then you have branches. So, at the junction you will not have parabolic velocity profile. So, there will be some there will be some error. Not only that, you may also have a local recirculation which will not keep it unidirectional flow. So, we have assumed only flow is along the z direction, but you will also may have some flow in the theta direction, at least wherever there is local recirculation. So, those things will give errors, but where we can still manage is that this is an integral form. So, integral form, the advantage is that if there are a few local errors, when it is integrated over the entire domain, that error is not significant. So, imagine that you are just try to relate it with your basic understanding of calculus. Say you want to calculate two things, one is a function f, another is integral f dx. So, when you have the function f wrong at a point, that means it is wrong, and the wrong may be very severe, but integral f dx, let us say at one or two points or a few points you have f wrong, but integral f dx is area under the curve over that entire thing. So, the total area under the curve may not suffer that much. So, that is why integral form engineers always like to use, because it somehow masks your ignorance about many things which you actually do not know, and integral forms are very popular, like boundary layer theory and so many other things people, that is why they prefer the integral forms. So, now you enter to a real scenario where you have a patient data. So, we are now getting into that how we can use the patient data to form either the 3D model or even the 1D model, that means geometrically and in terms of boundary conditions. Equations we have already seen. So, what will now be needed are the geometry, boundary conditions and properties. So, let us say you have this internal carotid artery. So, the carotid artery will have some branches and their names are written. So, why their names are important, because sometimes doctors refer to these names to really say where the flow rate, where the pressure. So, it is a good idea to at least recognize the names. We do not have to remember this as an engineering analysis, it is just some branch. So, now the interesting part is that, so you can smoothen and do all this. For a one dimensional calculation, what you can do is that you can forget about that 3D structure and just extract their center lines. So, that will be like a local 1D, and there is a open source software very popular which does it, known as SimVascular. So, the SimVascular will create that line diagram of this, and for each of these lines you can apply that equation. So, it is just like you imagine the complex pipe system as a network with a node and something is going in and something is going out. So, that you can use a kind of Kirchhoff's current law, voltage law type of thing. And the flow rate versus time at the inlet is given by the phase contrast MRI, which is for a particular patient, an anonymous person. This is Q versus time. These are all practical data from some humans, but that is what. Now, this is for the inflow. For the outlet, what you do? For the outlet, you do not have really anything, any information, and there are quite a few sort of branches through which it is coming out. So, it is usually split in three different for the carotid artery, three different branches, and as obtained from the MRI, it is one of the branches is 70%, another 25%, another 5% for the three branches. Total you will have 100% of the outflow. The mean pressure you can, you have no idea, but the artery's mean pressure you can get from the cuff blood pressure measurement, that is the classical blood pressure, or you maybe by a digital thing. So, for this patient it was this value, and typically what you require is not the average value, but the waveform of the pressure. Pressure has a variation of time. Now, fortunately for general human beings, I mean except for exceptions, that waveform is very similar. So, if you, so that means you have a sine function or a cos function, instead of sine cos it is something more involved, but such a periodic function. So, you can set up the function correctly if you know the mean and you can set the amplitude. So, that is set by that 90 millimeter. So, you with that reference you can set up that function, because that is more or less like universal, not really universal, but you can use an approximating function. The original patient specific pressure waveform, it is possible to know, but for that there is an invasive guide wire based procedure, very tough on a human. So, invasive procedure, and then from that pressure versus time is known. Usually no person will allow you to do unless sort of you are so in the mercy of the doctor. Say someone has heart attack and all, and doctor can do anything on the person to save the life. Otherwise normal human person will not like to go through this diagnostic test. So, this approximation by just the blood pressure measurement and using an approximate function, it may sound to be bad, but it is not that bad, because you have to see that in a non invasive way what best you can do. Now, at the outlet, the boundary condition, be it 1D, 3D etc., this kind of lumped model is used. As I told you previously and in one of the very early study maybe the first session, that due to the work of Otto Frank, the distensibility of the blood vessel was thought of, imagine like a capacitance, capacitance stores charge and this stores volume, and resistance is resistance against flow. So, there is accordingly the outflow has been approximated by a lumped model where you have two resistances R1 and R2 and one capacitance where C and R2 are in parallel. So, this is commonly known as RCR model, and it is very well established, and there are ways of calculating R1, R2 and C depending on what you get from the medical imaging and the blood pressure data. So, R total is R1 plus R2, which is the mean pressure by the mean flow rate. So, mean pressure is also measurable and mean flow rate is also measurable, because flow versus time you get from the MRI, phase contrast MRI. Physically R1 represents the proximal resistance, proximal means what is the close, and R2 is the distal resistance, and C the compliance, which is like the capacitance. So, R1, R2 and C is found by minimization of the target pressure wave and pressure wave estimated from this. So, this is how do you find this out? These are all artificial parameters. So, you have a pressure wave which is physically there for that person, and physically in a sense invasive procedure is exact, and by measuring the cuff blood pressure and then approximating it by the physiological function, that is also physical, and this 3 parameter model will give a pressure which is an artificial. So, the difference between these two, if you minimize, then whatever parameters R1, R2 and C you will get, that is like equivalent resistances and capacitance, which will give the same pressure profile. So, if you do that, so what you do is simply you use the Kirchhoff's current and the voltage law. So, you have the total voltage as, so if you see that whatever voltage is there in the from the left side, which is in the right side, you have the voltage across the, so in the right hand side what you see, Q by C into 1 plus R1 by R2, it is representing the voltage which is across the capacitor, and R1 into dq dt is the voltage which is the voltage drop due to the current in R1, because current is dq dt. So, sum of these in the right hand side is the total voltage drop, as you, if you are traversing the path, the current the charges are flowing along R1, then the charges are stored at C. And similarly in the left side, the same is the voltage across this, sum of these dp dt, which is that you have the node, the first node, and then if you imagine that the flow path through R2, then that is P by CR2. So, irrespective of the flow path, the total voltage drop is the same, and that is how they are equated. and Kirchhoff's current law, total current is the sum of the currents that are there at the junctions of these. So, if the total current is flowing Q, that is the right hand side, the left hand side is distributed, one going to C and another going to R2. Okay, so, this is what it is, and then you do all the this algebraic manipulation and you get a differential equation, and you can integrate it by an integrating factor, because it is like dy dx plus py equal to q. So, if that form of ordinary differential equation, you can use an integrating factor, and with that integrating factor you can get an expression for the pressure versus time, where the parameters are R1, R2 and C. So, your objective is to make this pressure versus time match with what is measured from the person, and then accordingly fix up R1, R2 and C by that method that I talked about. So, once you know that, then you have a fluid structure interaction problem if you are solving a 3D problem. I am not going to repeat this because we have discussed about this extensively. So, you have a fluid domain, you have a solid domain, and what is done is that if you are considering the fluid and solid domain as continuous, whatever is the interface force between the fluid and the solid, that you dump in the form of a body force in the solid mechanics, which is the surface traction divided by the wall thickness, and the stress strain is linear for the solid. So, it is linear elastic, and for fluid this is Newton's law of viscosity. You may argue that blood is a non-Newtonian fluid, so why Newton's law of viscosity? For large arteries that approximation is not that bad. So, always keep in mind that for large arteries it is the elasticity of the artery that should be your main concern, and for the small blood vessels it is the non-Newtonian nature of the blood. So, these are some results, so this is something what you can present to the doctor, the so called colored fluid dynamics. So, this is important because I mean you have to do two things. One is you have to give the doctor something useful, and you have to also give doctor something impressive. So, you cannot just sort of give some tables and very what you say blunt looking graphs. So, you give something like this, and with all the modern tools you sort of superimpose one image with the other and make a movie. So, doctor will see how this wall shear stress is changing with time like an animation, and doctor will say, wow, now this is an engineer whom I was looking for. So, and then as an engineer your job is not to make the doctor fooled, so that this value is correct and doctor is also impressed. So, this is the oscillatory shear stress, and this is how you calculate it. Why this is very important? Because this is giving a value of the shear stress sort of averaged over the time period, and that is very important because at every time it is not important. And then you have this displacement and wall shear stress. So, that is this how you impress a doctor. So, all these simulations, these animations going on, and with these properties. So, now the question is, well, you have put certain things, how good are these inputs? So, this result is quite good, you have done everything, you have taken medical image, you have taken flow from that, but properties you have not taken from that. Young's modulus, who will measure Young's modulus of the blood vessel wall, right? So, you can try to do an experiment on your friend, put some anesthetic and try to measure Young's modulus, good luck. So, if you can do that, so that is not there. Density of blood is more or less, yeah, I mean this is not very bad, whatever it is, and viscosity is like this is apparent viscosity, treating it as Newtonian over that is also okay, and wall thickness, this is also not that bad, but again it can be usually anything between 1 to 10 millimeters. So, 2 is something which is again some approximation. So, there are two important uncertainties, Young's modulus and wall thickness, and so whatever you get you have to at least tell your doctor very candidly that doctor, I have given these with these uncertainties. So, doctor will say then what I will do with this. So, you have to then give the doctor a feel that if these uncertainties were covered with maximum and minimum range, what would be the difference in the answer, and the doctor then will have a confidence that okay, maybe this is told that this is the answer, but even if it is inaccurate, this is the upper limit and this is the lower limit. So, we will see how that can be done in the next session, but if you now compare the 1D and 3D, see it is not that bad, and for rigid and deformable channels the the symbols are different, you can clearly see. So, there is a decrease in the peak value of the pressure with increase in deformability. This is qualitatively we observe, and the reason is that increase in the diameter of blood vessels due to increase in compliance reduces the hydraulic resistance. So, these are with values of density, viscosity and thickness as 10% of the radius. So, this is approximately the order of magnitude wise correct, local radius, the local thickness is about 10% of that, but again if you have plaque formation and all, that is a different thing altogether. So, to summarize this session, the full scale 3D and 1D reduced order modeling simulation of blood flow through carotid arteries is utilized to find out flow rate, pressure, wall shear stress, oscillatory shear index, etc. And 1D reduced order simulations, they could be completed in even minutes on a single CPUs. They could be practically very useful for healthcare, for real time prediction of what is going on for a particular patient, and you have indeed significant variations between rigid and deformable vessels. So, this gives the at least the justification of doing a fluid structure interaction analysis. So, we stop here in this particular session and we will move to the next session in about 5 minutes, where we will see that now that we have seen that what physics can do, we have also seen that what physics cannot do. So, where you do not know data, you are limited by your lack of data, although your physical law is correct. Physical law is Newton's second law, not that for human body Newton's second law becomes some other law, but because of your lack of knowledge in many complex matters which are there inside the human body, they are occurring, you are bound to get something which is not relevant to clinical practice. So, how can we convert all these and maybe some measurements that we do in the diagnostic tests on a regular basis when we consult a doctor, to make something which is more practically relevant for a doctor to take a decision, and that is where you will see how physics and AI can be combined, and that we will see in the next session.
Can't we calculate all these structural properties of blood vessel of an expired person?
Expired person, but that will not be correct, because when blood is flowing, there is a particular type of property. There is a difference between living and dead tissue, and mechanical properties are drastically different. So, in engineering there is no difference between living steel and dead steel, both are steel, right, but tissue, living tissue and dead tissue is very different. কালো তাহলে ওই জাস্ট একটা চিনি ছাড়া একটা কালো ওইটা নিয়ে
When you reduce model derivation, you told that the flow is because of the pressure difference and the wall shear stress, means that
no, not because of wall shear stress. The flow is due to the pressure gradient, that is it.
Yes.
Wall shear stress is resisting it. Wall shear flow is not due to wall shear stress.
but there should be minus sign if it is resistive.
It is symbolically that one. Now, when you put the plus or minus, it has to be, see you can, it depends on whether you have written tau equal to mu du dr or minus mu du dr. So, accordingly it is plus or minus. So, you have to see what sign you have used for tau, and then accordingly you write it. So, not a question of whether plus or minus, it is like how you have written wall shear stress. So, if you write tau equal to minus mu du dr, the tau is positive, but if you write tau equal to mu du dr, then that is negative. So, it depends on how you have written the Newton's law of viscosity. So, we go to the next session. Again, because this is a short course, we will give this overview, but I think this overview is very, very important for any modern generation researcher. So, this is the integration of AI and physiological flow simulations for what we call as clinical decision support. Clinical decision support means that AI plus simulation will not become a doctor or doctor's replacement. What it will do is, it will give some recommendation to the doctor and final decision lies with the doctor, and in fact from the legal point of view also, you cannot make a computer or maybe computing tool, even if it is through AI, as equivalent to a doctor. This is not permissible. So, you can at the most call it like a decision support. Now, when you talk about data science, normally people, so this is where people who have rich background in physics and applied physics, which is engineering, have a lot to contribute. So, normally data science, the people who are working on that, they are working on data where the physics is not the primary aspect, except for a few applications like atmospheric prediction, weather prediction and all those things, but many other cases it is like somehow data has come. Say in the fish market, what fish is being sold over a period of say 1 year and what is the type of customer, etc. So, that may be very interesting for analysis of how the business can develop there, and data science plays a very big role, but that does not have any conservation law, except for that for every person the monthly salary is conserved. So, in that way now when you have physics, the physics is something which governs data. So, there is a way in which you can get data even in a physical system, and you may get that data even if you are ignorant about the physics. So, when we were research students, we used to make fun of many of our friends who had access to very high end facility, and they will give some input and they will get some output, and they are very happy about it, that data is there. Sometimes we used to say that you change one material to the other, get a nice characterization, 20 graphs and then make a paper. So, you make it polish it a little bit, again 20 data and make another paper. So, we used to laugh, it is not like that, but what I mean here is that it is not about the science, it is about that getting data even if you are ignorant about the science. So, the question is, now this is a very interesting question. Say you do not know the science, you get only the data, can you retrieve physics from the data which you do not know? So, this is something which is really an open ended question, and why I have put it at the very beginning is because in human body physiology many physical things are also not known. So, could it be possible to get some hidden physics from data, and that is where limited physics with data combined and physics data talking with each other can be a good approach to at least make an attempt. But let us say, like when we want to really speculate what is going to happen if you have data but you do not know physics, we all have learnt in either history book or school level science book about this famous experiment that this Galileo's view of that irrespective of the mass all objects will fall equally from a particular height, and it will take time like that h equal to half gt squares physical thing. Now, in those days it was a cultural shock, because Aristotle's theory was that it will fall with speed that depends on their mass, and it is not wrong. If you see, this is from the natural observation Aristotle told. Aristotle was not an ordinary person, right, he was a great philosopher. So, then This is the famous Pisa's leaning tower experiment that we have all studied, that as if Galileo was sort of throwing ball from there and ball was falling down and time was being measured just to demonstrate. See, these things have been great sort of what I would say as iconic events, although in history there is a debate that this event might not have at all taken place. But even if it has not taken place, you take it as a spirit that there is something which is a belief, it is a strong belief, and science comes and questions that belief, and because it is a serious question, the person has to demonstrate in the front that yes, the belief is true, and it was there for quite some time a culture in the society for acceptability. So now if you do these experiments with different objects of different mass, say the typical one metallic mass and a feather, they will fall differently. You go to that Pisa's tower and fall and make it fall, they will fall differently. So then if that experiment is converted to data science based theory, then Aristotle's observation would be translated to a new theory, right. Galileo's theory will not be there. So what was the genius of Galileo's thought is that he somehow through his experimental analysis eliminated the effect of resistance, frictional resistance, be it air or be it anything else. So if that is eliminated, then only it is independent of mass, otherwise you have drag force which is related to the mass, right. So or the volume to be more specifically. So in that way what we can say is that a blind collection of data and churning it cannot retrieve physics, and you have to isolate certain effects to get into that physical law. So if those effects are isolated and an experiment is done, and after a lot of large number of such repeated experiments, perhaps a data scientist will come up with H equal to some constant into GT to the power n, where n may be 1.99999 or maybe 2.00001 like that, may not be that exact, but something which is quite close. So now it brings to this particular application that where from we left in the previous session. So patient specific cardiovascular simulation. So now if you recall the block diagram that we had the MRI data, we converted it to patient specific geometry and boundary condition, other boundary conditions we constructed from some RCR model etc., and then you have 3D and 1D as your domain and you get the result. I made a remark that you do not know whether the results are correct or wrong. So now we are going to do with something which one aspect of data science, that uncertainty quantification, that you have got data, you have got results, but how do you quantify your upper and lower bounds of error, and that needs a statistical analysis of this entire input output relationship. So just to make it a standalone session, this is a reproduced view of that patient specific problem that we are going to talk about, that you have some arterial segment, it is geometrically smoothened, and then you can also extract the center lines if you are doing 1D model, and then you use the inflow boundary condition from the phase contrast MRI data and outflow condition from that RCR model, fitting that with the pressure variation in the human. So now what are the sources of uncertainty? As I told, it is not possible to predict the Young's modulus of blood vessel using any invasive or non-invasive medical diagnostics. It is not exactly true in a sense that some invasive diagnostics it can be done. By this sentence what it means is that those kinds of invasive diagnostics do not exist in a real clinical practice, because patients will run away. So there are invasive procedures which are indirectly talking about that, like intravascular ultrasound, IVUS, for arterial wall thickness. So, it is something which is invasive and it has certain risks on the patient, of course expensive, and if you do an inappropriate segmentation of the image it can give an error. So, not that you get the image means you know the answer, because it is an indirect way of doing that by using the ultrasound. So, Young's modulus and the wall thickness are two very obvious uncertain parameters, but fortunately researchers have studied or what I would say not really researchers, physiologists and what you call as clinicians, they have reasonable experience on like what could be a range of these Young's modulus, and so typically with all those data somehow indirectly speculated from maybe invasive procedure and all, and if that is synthesized, typical mean is 530 kilopascal and standard deviation is 200 kilopascal with respect to a statistical distribution which is known as uniform distribution. Just like you have heard about normal distribution, this is uniform distribution where you know it basically you have equal probabilities of everything. So, you have no bias to anything, and so mean and standard deviation you can calculate from the lower and the upper limit. The thickness also has that one, and the thickness to radius ratio which is typically say mean 0.19, so about 0.2 roughly. So, ideally because these are uncertainties you should represent the uncertainties in your graph when you are giving a graph of say flow rate versus time or pressure versus time. So, how do we do that? I will give an outline of this method because the this course is not to that level that we can talk about the details. There is a method called as polynomial chaos. So, what this method does is that if you have any function f, any dependent variable like flow, pressure, wall shear stress, you can write it fundamentally as a infinite series with the product of two parameters. One is the beta which is a stochastic deterministic parameter, and psi which is a stochastic, that means something which depends on chance, and it is quite clear that what depends on chance here, the modulus of elasticity based outcome and the wall thickness based outcome. So, psi will be a function in this case, or rather yes, the zeta will have these two entities zeta 1 and zeta 2, Young's modulus and wall thickness, and psi will be a function of that. So, of course although infinite series, but you can like any numerical approximation you can sum it over a finite number of terms, say p, and that is the order of this polynomial chaos expansion. And there are ways of this estimating the beta and psi, and beta being the deterministic thing. So, that will not vary with change in data or uncertainty in data. So, if you have a solution of some Navier-Stokes equation, then it can contribute to that beta, and that you do not have to change if you want. So, to calculate beta you have certain integral expressions, and the psi's are some polynomial functions, and there are many ways in which you can do that. And typically once you get these expressions for f, the expressions for f will then be sensitive to the uncertainties in the Young's modulus and the Poisson's ratio, wall thickness. So, then you can, so that will be like a range of data depending on the variations in this zeta 1 and zeta 2. So, you can extract the mean and standard deviation from you can use certain inbuilt packages like in older days people had to write that, but with Python's different sort of modules. So, you want to plot the probability distribution, you can use the Seaborn package, you can, if you want to use this mean and standard deviation from this one you can use the chaos pi. So, in that way you have ready made things. So, if you now get your answer you will get the error bars, that means the upper and lower bound. So, when we talked about hemodynamic simulation without these uncertainties taken into analysis, that is that line, and the shaded region which is that sky blue color is your possible answer will always lie in this. So, if you now give this graph to a doctor for maybe flow, wall shear stress or pressure, the doctor will know that okay, maybe this particular answer is something, but it could be minimum this and maximum this, and that is good enough for a doctor, because for a doctor for most of the cases, unlike say engineering or physics, that exact decimal value and all these are not important. It is just like a broad range that on the basis of which doctor will treat. So, the blue region is basically mean plus minus 2 into standard deviation. So, the 2 sigma limit. So, now the interesting question. So, if someone tells that well you know the uncertainty in the Young's modulus, let us say we do not have any uncertainty in the thickness of the blood vessel, because that has uncertainty, but not as serious as the Young's modulus. So, Young's modulus we have seen that maybe if it is 530, then also it could be that plus 200 and minus 200, it is quite a range. So, let us say you do not know that. So, is there a way by which, by combining the medical imaging data and this uncertainty analysis, you can predict what is the Young's modulus of the blood vessel. So, this is a method which our students have developed, and accordingly this what is done is that it is like an inverse analysis. So, you get the output, and from the output you say you assume a value of modulus of elasticity, you get the output, and you may vary the input flow rate versus time till your input becomes same as what you get experiment at, that means by the medical imaging, and the corresponding modulus of elasticity then becomes the modulus of elasticity of the blood vessel. So, that this is called as inverse modeling. That means say you have a heat transfer problem, if say you are given the boundary condition and you find out the temperature. So, there can be a problem where you have measured temperature, but you have to find out the boundary condition, that is called as the inverse problem. So, there are ways of solving inverse problem, typically they are related to error minimization, that you assume something and then you get an answer and try to minimize the difference between you that. So, then so this is one way, but this is not the general way for doing everything, because for everything you may not have this kind of well structured governing differential equation. So, then how do you do it in a more generic platform where you do not have such governing equation, but you may have other equations also. So, this is a deep learning approach where one can use neural network. So, this is just a bit of summary I have put, although modern generation everyone will know what is a neural network, but just in case. So, a neural network is a computational model inspired by the way the biological neural systems work. So, it is a key component of machine learning and especially deep learning, where it is designed to recognize patterns, learn from data and make predictions. So, how do these networks work? So, certain terminologies I am just trying to emphasize, because these terminologies people very commonly use when they are describing the neural network. So, one is forward propagation. So, you have an input and that is fixed. Input is actually not called as a layer, in a sense that input is known. So, data flows from input layer through hidden layer. So, you may imagine just the situation like a black box. Inside the black box, like our brain is like a black box, we do not know what is happening, but we have some input and brain can synthesize and give some output. So, that input is a data and that data has to propagate to get an output, and when it actually propagates it goes through certain in between steps, and each in between step is like a layer. So, data flows from input layer through hidden layers to the output layer. Output is what you get, and maybe your data crunching or analyzing data from the experience, that is the training, will be more if you have more number of such hidden layers, but that again will make it more involved computation. So, each neuron, I will come to a schematic subsequently, what it does? It calculates the value of output as a summation of a weighted value of the input, and so summation of Wi xi plus a constant, or it is not a constant really, plus a parameter which we call as a bias. So, the network computes the error then by comparing the output to the true value using a loss function. So, loss function is nothing but a way to see that whatever is your prediction from the data, how much it is differing from the actual solution, and why you do that is because once you find out this loss is an error, a way to minimize this. So, how it does is simply it adjusts the weights and the biases to minimize the loss. So, if there is no rule game or no experience, people will do it by sort of just heuristically, that let me increase the weight this, decrease the weight this, and this has a system to do it. So, gradients of the loss are compared with respect to the weights using the chain rule via back propagation and optimized using certain algorithms. Typically the stochastic gradient descent or ADAM, very common algorithms, and usually nowadays what happens is that even if you are not very much sort of conversant with the details, there are so many open source packages or codes, you can simply use it, but you must know that for what purpose it is used. And then you have iterative learning, you have forward and back propagation, they are repeated over many iterations which are called as epochs, until the network learns to produce the accurate outputs. This you can verify by some test problems where it gives the correct thing. So, just a terminology. So, you have the neurons which are the nodes. So, you can see the input data is flowing to the neurons and the nodes. So, these are the basic units of a neural network. Each neuron receives inputs, applies a weight and bias and passes the result through some activation function, and there are standard activation functions. So, you have the input layer, the first layer that receives data, which we normally do not technically consider as a layer, but it is termed as a layer. Hidden layers between the input and the output, you see the second diagram where you have the hidden layer. So, where the computations and transformations happen, and output layer, the final layer that produces the output. Connection, each neuron in one layer is connected to neurons in the next layer. These connections have weights that determine the importance of each input, right, and see how it relates to a clinical decision. So, let us say when a patient comes to a doctor, there may be 10 factors that the doctor is analyzing in the mind. Out of that, the doctor has a priority of the importance. So, some factors will have very less importance, some factors will have more importance, and here those importances are systematically assigned through weights. Activation functions, these define how a neuron processes the input data, and you have common examples like ReLU, sigmoid or tan hyperbolic functions which are very commonly used. These are all smooth functions, if you see that they are transiting from one to the other. Now comes the use of physics, where it is like a CFD solution. So, this brings to the context of something which is known as a physics informed neural network. So, a neural network which does not just do data crunching, but the data crunching is done with the help of certain physics based simulations, where the physics based simulations will have some practical inputs, just like the medical imaging trained input. So, a physics informed type neural network is a type of neural network that incorporates physical laws typically represented by the partial differential equations, which is our Navier-Stokes and that Navier equation whatever. So, by doing this can learn solutions that adhere to the underlying physics without requiring a large amount of labeled training data. So, usually if you do not know the physics, you may have to train the neural network with a huge data, so that even ignorance of physics is made up by learning from the data. But if you now combine your physics with realistic data, then with less amount of training you can make your neural network predict very well. So, this is an example of what you do for Navier-Stokes equation. So, what is written here, a bit of mathematical notation, because usually mathematicians will work on this, but just take it physically, that the capital F, the set of PDEs which form the backbone of this physics informed neural network are the continuity and the momentum equations, okay. And usually you take everything on one side and set right hand side equal to 0, because your error is measured by deviation from 0, which is called as residual. So, you have I as the initial condition and B as the boundary condition, it is sort of symbolically written, and theta is some parameter in the real space. So, now if you see that you have an neural network structure and it has a prediction of values, but you want to minimize the error between what you are saying and what Navier-Stokes equation is saying. So, to do that you have to calculate the partial derivatives. So, there is something called as automatic differentiation. So, you have the parameters, you have to find out the partial derivatives which are there in the Navier-Stokes equation, and automatic differentiation is something between symbolic differentiation and numerical differentiation, it tries to take an advantage of both, and then you can calculate some error which is conceptually the difference between what your automatically differentiated values will give when they are substituted in the Navier-Stokes equation and the CFD solution of the Navier-Stokes. That is not automatic differentiation, that is a standard numerical procedure. So, the advantage is that you do not require large data sets and physical laws will guide the training like the Navier-Stokes equation. It has a flexibility to handle high dimensional problems and direct incorporation of boundary and initial conditions, and ability to generalize to new scenarios. So, new scenario may be say from pipe flow you are going to a very complex domain, but physics is the Navier-Stokes equation. So, that remains the same. So, now how to implement all these, and this usually someone who is learning the subject from the beginning will think that, oh, it is so difficult because I have to code everything. Now fortunately you have this TensorFlow, which is an open source machine learning framework developed by Google, and it is widely used for building and deploying machine learning models including deep learning, and it can offer tools to work with a variety of tasks like neural network, data processing and distributed computing. So, anyone who uses this as a tool, so everyone who is sitting here, I would imagine that nobody is a theoretical data scientist. So, all of us, if we have to use data science, it is from an applied perspective. So, we cannot be fundamentally as strong in data science as someone who has the theoretical thing as their subject. So, for our case, in most of the scenarios, if we have understood it, then for implementing, if we have something open source, that is quite friendly for us, and fortunately, and also you have many other Python tools which you can use. So, TensorFlow, these are certain features. It is an end-to-end machine learning program. So, it supports everything from defining and training models to deploying them across various platforms. It could be mobile, web or cloud. It is easy to use, and it has high level APIs, that means basically communication between the various simulations. It is scalable, it can train models on CPUs, GPUs, TPUs, the TensorFlow, the name comes from the fact that it is something which is more generalized than a vector type of thing. So, you have different layers and the data is flowing from one to the other. So, that is why the flow. So, tensor and flow combined together is like TensorFlow. It supports different machine learning and deep learning tasks like regression, classification, reinforcement learning and generative models, and it has lots of visualization tools which you can use like TensorBoard, and it can be deployed across a range of devices including servers, mobile phones, embedded devices and web browsers. So, now with such a kind of open source thing, let us say you are developing your first exercise for deep learning for a fluid mechanics problem. So, what do you do? So, mathematically the ANN, that artificial neural network, can be described as a direct graph which is composed of a group of vertices representing neurons and a group of edges representing links, that is as per the graph theory. So, as we have seen that usually this is represented by ZL, which denotes the hidden layers between the input and the output, and L is the index of that particular layer. It is a function of the weight times this ZL minus 1, like a recursive thing, plus the B, which is your bias function. So, the FL which denotes the activation function will make sure that your new value of Z in this layer, how it is mapped to the old in the other layer, and typically you have different functions like sigmoid, ReLU and tan H, etc. So, quite simple to code as such, but there are open source things, and since only weight matrices and bias vectors are to be trained, that is W and B, the computational cost can be neglected as compared to the traditional numerical. Now, think about all our traditional CFD. So, conventionally the deep learning is for solving fluid dynamics problems by building up this input and output relations. The solution can be calculated by a black box surrogate model, that means it is like input output based model such as a fully connected neural network or and maybe this convolutional neural network, and all what you get is your F, which is the exact solution of the fluid mechanics problem, which includes the velocity and pressure, that is approximately this F tilde, and it is obtained by using some local minimization principle, error minimization principle. So, that means you have a loss function which you want to minimize. So, this is a particular, say a very nice loss function which actually the problems, some of the problems that my students are using, I find this is quite good. It is, you have a, so you can see the first is that error due to that initial and boundary condition. You have the error due to what you have in the Navier-Stokes equations, you see all terms in the Navier-Stokes equation written in one side, and error due to inaccurate mass conservation, that means say somehow your approximate solution is not satisfying the continuity equation. So, some of these is a loss function. This is one, see there is no hard and fast way, you can construct loss functions in many ways. Sometimes people, so this is like a more physically based loss function, because what you want to see, you want whatever is your solution, you want to make it satisfy the governing equation, initial condition, boundary condition for the momentum and also the mass conservation. So, all of these you want to satisfy, so that error you are minimizing. The first and the second derivatives of velocity and pressure are calculated directly by automatic differentiation. So, it is a method between symbolic and numerical differentiation. Numerical differentiation emphasizes directly substituting into numerical approximate solution, that we all know, I mean from your numerical analysis, and symbolic it emphasizes on solving algebra directly before substituting the numerical. So, automatic differentiation applies symbolic differentiation to the most basic operators, not all operators, like a constant, power function, exponential function, log, trigonometric function, but not all, and then substitutes that into a numerical value retaining that intermediate result and finally apply to the whole function. So, it is a sort of a hybrid, partly it does symbolically and partly through numbers. So, this is the overall flow. So, you define the governing equations, you have a neural network architecture where you choose a fully connected with some spatial and time coordinate in one of the outputs, you calculate the loss function. So, this is just one example of the loss function where the input output is the initial and boundary conditions have no uncertainty, they are all well. So, you are minimizing the error due to the inaccuracy in solving the representing the partial differential equation and mass conservation this deficit. But if you have the boundary condition effect, you just simply have to add it. So, in general you have the loss function due to the physics, boundary and initial, and the training data use sparse or no labeled data, instead sample points in the spatial temporal domain for enforcing the physical laws, which are just collocation points, we say the points where. So, these points are like note points or grid points where you satisfy the physical laws. Optimization, use certain optimizers, I will show one, the Adam optimizer, and evaluation, you compare this solution against the CFD solution, and that is your sort of standardization. How will you standardize it? Sometimes instead of CFD, if you have very dense experimental data point to point, that also you can use, but such experimental data is not easy to get. So, what you do overall, say you have a sample problem, this I have taken from one research paper to give you a visual idea. So, you have a residual block where you have hidden layers with weights and bias, you have output layer. So, you do that automatic differentiation and then you calculate that mean square error, because dealing with the mod is very difficult. So, you do the mean square error, and then if the error is still there, you keep on doing it. So, how do you know error is there? You validate it with the actual CFD solution, and in that way you keep on training it until you see that your validation is doing quite well. So, usually you need more sample points if your neural network has to be very accurate. So, this is a very interesting example on an equation which is a simplified equation known as Barger equation, one simplified version of the Navier-Stokes equation. So, this blue colored thing is loss function based on purely data, that means no physics, and the green is the loss function based on the physical model. See, as soon as you have put that physics and informing it to neural network, see how less the loss function is coming, and that is where the importance of putting physics in the data science. So, the Adam optimizer, I will not get into this because it is a bit involved for most of you, you will require a bit of mathematics training to do that. So, it is based on something which is known as a moving average calculation. So, what it tries to do is basically to minimize the error by an optimization principle. It is a stochastic gradient based optimizer that adapts the learning rate for each parameter during the training. That means during the training, like it is something like evaluation of the training. So, someone doing a class, say a junior class student, so what is the rate of learning, you do some evaluation and you try to see that the rate of learning is the maximum, so that the learning and the exam performance are compatible. So, you have a gradient which is the derivative of the loss function with respect to those parameters, the first moment which is the mean, the exponential moving average, and the second moment is the exponential moving average of the squared gradients. So, exponential moving average has a standard statistical expression to calculate, and I have put those expressions, not that you have to very much a master of that, but at least as I told, that is good to know what is there instead of just taking it as a black box. So, now we come to a few maybe 2-3 final examples which I will just browse through to give you an idea that what this can actually do in terms of a game changer approach in the clinical world. So, when a doctor is treating a patient, what the doctor does? So, you go to a doctor and say that you have headache, and as a patient can be as vague as possible. So, that is the right of the patient, and the doctor has to somehow bring important observation or inference out of that. So, doctor knows that patient is telling that there is headache and it is and nothing else, and saying that feeling uneasy, all those very vague things. So, doctor knows very well that headache could be maybe for 1000 reasons, starting from simple migraine to brain tumor, that could be possible. But unlike Dr. Google, doctor will not give the most impactful search at the beginning, oh you have headache means I think you have brain cancer, right. Normally no doctor will tell this, unless a very sadistic cynic doctor. So, then what does the doctor do? So, doctors do some mental exercise, which sometimes loosely I say human AI. They do not have an algorithm, but through experience and knowledge combined everything they do. So, what the doctor will do, in fact a good doctor will see your body language as you are approaching him or her sitting and talking. That is also a data, because that talks about your physical discomfort or maybe mental discomfort, whatever, and sometimes they are connected. And then doctor will talk about your medical history, either it is available or maybe ask whether you are able to give correct answer or not. Maybe sometimes I have seen doctor is asking, do you have anyone in your grandparent who had diabetes? Now answer cannot be given, say in those days nobody used to do blood sugar test. So, maybe my grandfather used to have 10 rasgullas together, that does not mean that he did not have diabetes, simply it was not detected. So, very difficult to say. So, something you have data, something you have no data, whatever it is you have some history, family history or medical history, you have symptoms which you can clearly spell out, and the doctor's office maybe it is whatever is the resource, some basic measurement and physical examination can be done, that is why a doctor is there. So, blood pressure, pulse, oxygen saturation, say you are having some pain somewhere, so doctor can press it and see what it is. So, these are kinds of things doctor can always do. So, with that as an input, doctor somehow decodes and says that out of that 1000 maybe 900 cannot be true. So, that 1000 is reduced to 900. Then maybe doctor will get into a few more measurements. So, all of us have experienced this, you go to a doctor, sometimes doctors does not do any experiment, even does not touch you, but has a broad idea and gives you something. So, sometimes doctor will do say more another level and then do in that way. There will be a situation where the doctor is not going to progress further, says it could be out of these 5 cases. So, commonly what the doctor then does is give some initial medication, wait and watch type of thing to observe and then rationalize. So, one way of doing it quickly is to do diagnostic tests. So, if you have the diagnostic test information like that cardiovascular tests, and if you have also the CFD constructed out of that and you also have data, then you have everything. But everything is not required, that means a patient who just casually thinks that the patient could be a cardiac patient and you start doing MRI and all those things, this is not a good idea. It is, even if the patient has money, it is a loss of resources. One of the very big cardiologists in Kolkata, head of one of the big hospitals, we do some work with him and he told that it is a great problem, it is a fancy of people who have money to do checkup when checkup is not needed. See, checkup means what? You can do some simple thing, but because maybe their office is reimbursing, they will say do MRI, do this, that and all. And so, this is something which is a wastage of resource. This is a problem of being rich. There is a problem of being poor and there is a problem of being rich. So, then that resource could have been used for another patient. It is not a question of money. See, the machine hour per day is fixed, and there may be an emergency patient waiting for that, for getting the life support. So then what you do is you subject that any patient comes, say you have the front office of the doctor, front office typically a nurse or a front office person. So we will get some data and use the neural network, I mean there is a app with some weightages, and we will say simply red flag or green flag. So green flag is jao bhago, so you go away, nothing is required. So some people when they go as patients, they feel very unhappy if no prescription is written. So some doctors play with the psychology of the patients and write what we say as placebo medicine, something which will not work, but some nice syrup and all, typically children will be very happy with that. So then then the next level say red flag means not that you bring that patient to the MRI table, right. So you will go layer by layer, do things, and in that way you screen patients to an extent that for the most advanced of what is required you really go for that which is needed, and then till that layer whatever has been done, every data is available to the doctor. So doctor no more has to be a doctor as great as Dr. Bidhan Chandra Ray, who out of just imagination will be able to understand what the patient is doing. So the doctor has all the data, and in a very limited time doctor can approach the data, maybe that CFD simulation and all, and come up with a recommendation for which the doctor does not have to apply so much of wisdom and experience. So this is something which we applied, and not in a complete sense, these are all ongoing works in our lab. One we started with this in the COVID period, the acute respiratory distress cases which were coming into the picture. So at that time our group was working with a machine that we developed known as COVIRAP. So a rapid detection of COVID using a you can say portable PCR like test. So then but this is not as accurate as RT-PCR test, so it gives an input. But there are many patients for whom whether it is COVID positive or negative something, but they were having respiratory problems. So that is a crisis. There were many asymptomatic COVID patients, so they did not have much of symptom, okay, you could wait. But someone is grasping for life is a different thing. Now you test for COVID for after 48 hours from the PCR lab result would come, typically in the second wave it was like that. So then what you do? So and we found that actually if these patients were done CT scan of the chest, the CT scan score and all those things will give good things, useful things. But in a resource limited setting in a village you do not have CT scan, at the most you have a portable X-ray. So we try to develop a neural network based system where we try to train the predictive capability by training the data of the digital X-ray with the CT scan data of the same patient, and develop this predictive model. And then we developed an app which will then take just the image file of the portable digital X-ray and get a risk categorization low or high. Now if you combine that with that point of care COVID test and maybe other symptoms, you can quickly come to a recommendation that whether the person requires life support, oxygen, and also you have the pulse oximeter data anyway, and then not only that, this may guide how much oxygen flow is required for that person, and that can be automated to some extent. So you can see that with all the technology being input to such a scenario, how it can dramatically change patient care where resources are not there. Every place is not ICU, and everyone should not be admitted to ICU. So that is what. The cardiovascular, I have talked about this, and I would just summarize here that you have the cardiovascular data where you have what you have as the data which comes from CFD. Our research group also has developed certain diagnostic tests where you can use finger prick blood and on the strip you put it, and with the smartphone you get results for maybe in this cardiac case blood sugar is very important, because chronic diabetic patients will be susceptible to many comorbidity scenarios, and also we have a lipid profile test. So again you take finger prick blood and put it on a mini disc and make it rotate. So lipid profile like LDL, HDL and triglyceride are very important for this cardiac health. So that these are simple point of care test. So in that way when you have all these things, you can combine that with patient symptom and history to make a stratified cardiovascular risk analysis with quantified numbers. And now if you give it to a doctor as a medical record, then doctor will apply experience or whatever, but this remains as a ground quantitative data and not much like heuristic thing. Another example, so we developed a technology which is which can do oral cancer screening, and this is very important for a country like ours where there are two common reasons of oral cancer. One is that HPV virus infection might lead to that, where you have really nothing else much to do about that, but a major part is due to the tobacco product consumption related. So now when these patients are there at the rural place, they are mostly unattended, and initially there is a pre-cancer and it progresses and eventually it gets into cancer. So if somehow they could be detected early, even before the cancer onset, it could be reversed completely. So you have this torch like device. It is actually a thermal camera, but what it does is it is a fluid flow problem in a sense that it measures the temperature in that, you can say, lesion, maybe there is some small tumor like thing, and that is input into a bioheat transfer code. And here you have temperature, as I was telling, that from the temperature you are having an inverse numerical simulation to map the blood perfusion, because a tissue temperature at a given location is related to the local blood flow rate at that. So you get a complete quantitative mapping of the blood perfusion, and blood perfusion is related, is well known to certain disorders, typically cancer, because cancer onset and progress will have a change in vascularity, and that will lead to that. And of course, but it can be very general, like for example people may have different blood perfusion not because of cancer or pre-cancer, but something else, and that is the whole challenge for anyone. And even if you look into these patients, I mean we have worked with such data, so we know very well. So these are two different cases, oral submucosal fibrosis, which is the right hand side which is written, it is known as pre-cancer, so it is not cancer, and oral squamous cell carcinoma is a cancer. From one to the other, it is simply a epithelial to mesenchymal cell transformation, which is a biological event, but sometimes visual impression wise even most experienced doctors will find it very difficult. So then you can apply this kind of thing, but you have to train it with machine learning with the features of biopsy taken from those people who have either this or that, and maybe a third type of person who have neither of these but maybe similar appearance because of fungal infection or something else, nothing to do with pre-cancer and cancer. So this work we did with the help of Guru Nanak Institute of Dental Sciences and Research, which is located in our same state, and then we put it up to a clinical trial phase 1 with 60 number of such people. We did this work round about that time when COVID was coming, so getting such work done was getting increasingly difficult, and but with those 60, 59 we could predict exactly what those not training, the validation, what exactly the biopsy report was telling. Only one this was not correct. So and there are certain cases where we could resolve the clinical dilemma, that means doctor seeing is confused whether it could be normal or pre-cancer or cancer, and this machine learning based thing, it could give an interpretation. So once we developed this, we got a lot of interest from many people, including mostly the people who do this dentistry work, that we want an app which will do this basic type of screening, and then the advantage is that it can give a complete overview. So what we did is here we combine that something we get the data from the person without subjecting to anything invasive, just conversing, observing and taking the image, or just by comparing with something which is known. So in that way just the user can make a tick and you have some weighted function, and then if you find that there is a vulnerability, then you apply this. So, with that multi-layer screening, with after all these, if you see that there is a risk factor, then you straight away send that person to a very qualified doctor. You say that no more the app of this simplified system. So, in that way you have a multi-layer clinical decision support model, where you have the clinical metadata, essential body signals, essential body fluids, and maybe a CFD solution. So, all this is called as multimodal data coming from different sources. So, usually if you have unimodal data, you can make mistakes, but if a lot of cross things are talking about the same type of interpretation, usually it has a chance of being correct. So, that approach can give a one data approach, where you have an individual, you are getting sort of different inputs for the patient. So, we have not talked about other types of computations which can be done, because it is not a part of physiological flow, but say genomics. Human genomics computing is also a very important area that can be done, but because it is not a part of the course, we are not talking about that. So, in that way you can get a complete, you can say, biobank with an individual, where all the details in the form of data are available and they can be synthesized to give predictions. And it is, I think, a dream for not just a patient or a doctor, but maybe the government, to know about the health map of people, and even the insurance providers who fix up the premium for insurance. So, in a way the whole idea of talking about this was that how a combination of physics and data, and maybe measurement and data analysis, can actually make a dramatic change in how this healthcare system, how it can function. Okay, there we stop here now, and we will have the break, and I think second half we will have the remaining classes. So, if you want to meet me for any reason tomorrow, I think in the first half you can meet sometime, because you will have lab class etc. along with the theory. So, whenever you are there, I will be available at my office in general, and you can